Continuing on this quiz, we have a relation here which is made up of 1, 2, 3, 4 points. These are 4 ordered pairs, which is one way to give a relation. And if we were to graph it, which might be helpful here, we would just plot 4 individual points. For example, 1, 2. Well, I think we're going to have to change our scale so we can fit things in. I'm going to call this 2. That will be 1. 2, 4. There's 4, 6, and 8. 2, 4 would be there. And then we have 3, 8 and 0, 1. 3, 8, which is right there. And then we have 0, 1, which is right there. This is all we have. We don't have any curve connecting them or any line segments. So it's really just made up of 4 individual points. Okay. So the first question is, what's the domain of R? The domain of R is the set of all x's, or the projection onto the x-axis of your graph. And we would get a dot at 0 and 1 and 2 and 3 if we projected. Or even easier, we could simply strip off the x-coordinates, 1, 2, 3, and 0. And remember, sets, order is immaterial. If we looked at the range, we could just strip off the y-coordinates, 2, 4, 8, and 1. And they are sets. And again, the range from the graph would be to project onto the y-axis. So we would have a point at 1 and 2 and 4 and 8. Is our function? Well, it's a graph, and we could simply apply the vertical line test, and it's clear here that the graph passes the vertical line test. The answer is yes, its graph passes the vertical line test. Now, if you didn't have the graph, alternatively, you'd have to look up here, and you, for example, could see that there are no points with duplicate x values, and so there can't be a case where we have the same x corresponding to 2 different y values. That is, the way a graph can fail. F is a function if and only if for every x there is a unique y value. That means you can't have something like 1, 2 and 1, 3. This would correspond to a point right above 1, 2 and failing the vertical line test. Or alternatively, f would be sending 1 to both 2 and 3, which is fine for a relation, but doesn't make a function. So its graph passes the vertical line test, or each y is unique with respect to x. Now, what's the inverse relation? That's simple. We could take this graph and reflect it across the line y equals x. And remember, the line y equals x in this picture is actually fairly slanted because my scale isn't the same. Remember that it's only a 45-degree line in cases where your scale is the same in both directions. So the picture might look a little funny here in our reflection, but we could certainly take 0, 1 and go to 1, 0, take 1, 2 and go to 2, 1, take 3, 8 and go to 8, 5, 6, 7, 8, 3, and we would get a picture that would look like these 4 dots reflected. Well, the easiest thing to do here is to simply take each point and interchange x and y. That is the reflection across the line y equals x. 4, 2, 8, 3, and finally 1, 0. It's easy enough to do this without a picture. Is R a one-to-one function? Well, looking at the graph, you can see it is, because its graph passes the horizontal line test. Alternatively, you could say that each x is unique with respect to y. That is, for each y there's a unique x. Or you could notice that the inverse is itself a function. And if the inverse is a function, then it and the original function are both one-to-one. Now the domain of R inverse, this should equal the range of R, and in either case we're going to get 2, 4, 8, 1. Whether we look up here for the range of R or whether we look here for the domain of R inverse. Now the range of R inverse is the, of course, domain of R. Remember, we switched the x's and y's. The domain is a set of x's for this graph, which turns out to be a set of y's for the inverse. Here we can see it's 1, 2, 3, 0, and again, order is independent in sets. Okay.